So the first thing that example 1 is really good for is for us to find out the difference between these two words, verify and prove. We've done proving already. So you've been working on that sheet. And have they been getting a little bit more difficult as you go? Okay. So we've done some proving. We're going to look at what verify is and what it means, and how you would do a verify question as compared to a prove question. So for A, they have secant theta times 1 plus cos theta equals 1 plus secant theta. We're going to verify it first. So in a verify question, we're going to verify theta equals 30 degrees. You still split it, or still rewrite it first, I guess. Rewrite secant theta 1 plus cos theta equals 1 plus secant theta. Still split it and draw a line where the equal sign is. And now with a verify question, you actually plug in the numbers. So we would have secant of 30 degrees times 1 plus cos of 30 degrees equals, on this side, and there's no equal sign, on this side you'd have 1 plus secant of 30 degrees. So it becomes a pie plate question. The nice thing about Chapter 7 is if you got a verify question, you'd be allowed to use your pie plate on your test or quiz. What is cos of 30 degrees? Square root of 3 over 2. So here we would have 1 plus the square root of 3 over 2. If cos of 30 degrees is the square root of 3 over 2, then secant of 30 degrees is 2 over the square root of 3. And over here you would have 1 plus 2 over the square root of 3. So a verify question is like a proof question with one number. You still have to make these numbers look the same on both sides. So you're going to want to write your final answer as a single fraction. What could I do? Well, what would you like to do first? Would you like to add these fractions or distribute? Add? Okay. So if I add first, I would need a common denominator, which would mean here, this is 1 over 1, so I'd multiply this by 2 and this by 2. I would get 2 over root 3. Adding these fractions together would be 2 plus root 3 over 2. Correct? Close my bracket. Now I have a fraction times a fraction. How do you multiply fractions? Multiply the numerators, multiply the denominators. So I'm going to get, or do you notice anything? If you were multiplying, do you notice that these 2's, like this would be grouped together, but those 2's are common factors and we're multiplying, so you could simplify it, which would leave us just with 2 plus the square root of 3 all over the square root of 3 on my left-hand side. On my right-hand side, if I wanted to add fractions, I'd need a common denominator. What would my common denominator be? Square root of 3. Now I have a common denominator. It'll be over the square root of 3. Add the tops. Root 3 plus 2. Are you okay if I write 2 plus root 3? Just so it really looks the same. Therefore, the left side equals the right side. And we're all done. Ooh, I don't like my shading on that one as much as normal. So that is a verify question. So you now know that they're equal only for one angle. Verifying is really mostly useless, okay? Because you just showed that it worked for one value. If we went to prove, if you prove it's true, it means it works for all angles. 30 degrees, 40 degrees, 71.8 degrees, all of them would work. So a proof is much more powerful than verifying. However, sometimes on the final exam they say verify, so we do have to practice it. And verify is the same idea, just with numbers rather than with values. So for the proof, if we want to prove it, we would start the same way. Secant theta, 1 plus cos theta equals, I think I know what you want to say. Okay, go ahead. What?
So, if it asked for a verification, but you proved it, wouldn't that prove the verification?
Yes, but they want you to plug it in. And yeah, totally. Yes, a proof shows every one works, so therefore it verifies every single one. But if they're verifying it for a certain value, they want you to plug it in and show your skills with the numbers.
So we would not get a mark for it if you proved when it asked us to verify it.
They want you to plug it in and verify it. It is still good arithmetic skills that you would be practicing. Okay. How do I want to prove this? I'm going to start with a little bit of a longer way and move towards a quicker way. There's more than one way to prove something. Okay? Would you agree that you could change secant to 1 over cos theta? And I like this because then my left-hand side of the equation, and if I do the same thing on my right-hand side of the equation, they're the same. I have only cos now, so there's probably a good chance that I get things to be the same. In fact, your main strategy in this unit will be changing to sine and cos and getting things to a single fraction. So if I do that right now, my right-hand side, not a single fraction. This is 1 over 1 plus 1 over cos. I would need a common denominator, so I'd multiply this by cos and this by cos to get a common denominator, and then I could add the tops. That's now a single fraction. Okay? On this side, I could distribute this and this. This would give me 1 over cos theta plus cos theta over cos theta. I have a common denominator already, so I could add the fractions to get a single fraction. And they're the same. There we go. Very nice. And you're done. We've proven it, and we made both sides the same.
How did you go from brackets to fraction?
From here to here?
Yeah.
Okay, I distributed. What's 1 over cos times 1? 1 over cos. What's 1 over cos times cos over 1? How do I multiply fractions? 1 times cos, cos, cos times 1, cos. Okay? So now I specifically, strategically did things in this question to make my proof single fraction in the end change to sine and cos, because that's the most important strategy. But being that it's the most important strategy does not mean that it's the quickest strategy or that there are better proofs out there. So now I'm going to just erase this. And I'm going to distribute to begin with. Can you see that that would give me secant theta plus cos theta times secant theta? And then secant theta is 1 over cos theta, which would make those cancel. I'm left with 1 plus secant theta, so I'm done again. It's a different proof. I didn't have to change anything on the right-hand side this time. How do I know? Well, when you've done many proofs, okay, especially if you've done a proof and it's taken a long time, sometimes it's not bad to go back to that same proof and say, is there another way that I could do this to make it quicker? And if you can see another way that would make it quicker, then you start to see patterns and just do proofs in different ways. So we're going to see when we do a bunch of proofs, I'll often say, hey, here's one way, here's another way, here's another strategy. Sometimes there'll be even shorter strategies that make it even quicker. But no proof is wrong. If you're like, oh, do I get deducted if my proof is wrong? No. If it's right, and I've had people go in circles for like a page, right? You can, oh, here's something from grade 10. Here, I'll show you. I'll pause the video. Let's look at B. Do you want to do the verifier or do you want to just do the proof? Okay. Oh, I like doing this proof. So let's just do the proof. You can verify. It's plugging in numbers. It's the same thing. You might have to rationalize denominators and things like that. All right. I'll do the sine and cos way first. Okay? So doing the sine and cos way and getting a single fraction, tan would be 1 over sine theta over cos theta. I need to get a single fraction, so 1 over 1. Okay? Should I make an E3 error? It's so tempting to do that. E3 error. What did I forget? Didn't write the theta. Even in your work, something small like that. One little place you forget the theta is an E3 error. So then I've got a common denominator. This side will be cos theta minus sine theta over cos theta. That's a single fraction. I'm going to try to accomplish the same thing on the other side. Get a single fraction with sine and cos. So I can change cotangent to cos over sine minus 1 over cos over sine. Now if I'm dividing by a fraction, I first want to have one fraction in my numerator divided by one fraction in my denominator so I can multiply by the reciprocal. Right now I don't have one fraction in my numerator. I would have to take this 1, get a common denominator. Again, when showing my work, I'm going to leave a little bit of space here. So my top fraction is cos theta minus sine theta all over sine theta. Bigger line here for my main fraction line. Cos theta over sine theta.
So why do we want it in terms of cos and sine?
Well, as a strategy, if we change things to cos and sine, and we get things to be a single fraction, I'm going to tell you in this unit, 95% of the time, your proof will be done. So I'm almost got a single fraction on the right-hand side. And people like this strategy because it's systematic. It's easy to change things to sine and cos, and then if you know your fraction rules, it's easy to get something as a single fraction. Fraction divided by a fraction. Multiply by the reciprocal. At this moment, before I multiply it out, I might put brackets around this to say that that's grouped together with that subtract sign. But now everything is multiplied, and I notice that these factors are identical, so they can be simplified. And now when I write my final fraction, cos theta minus sine theta over cos theta, so as far as my thinking goes, I've been very systematic. I changed things to sine and cos. I got a single fraction. I now look where are things at. What's my left side? Oh, I'm done. Therefore, left side equals right side. QED. I'm done. I tried to act surprised. I knew I was done. I knew I was going to be done. But did it sound surprising? Yeah? It was good? Believable? Good. Right? I've been working really hard on like acting. Do you guys think I like math? Yeah? Okay, good. Perfect. It's been working. Right? Every night I go home and swear and like she just about spit over her whole nose. Okay. Good. So we're done. So this was change things to sine and cos and get a single fraction. A very good strategy because it works almost all the time. Sometime we're going to get into more difficult ones where you're going to have to add some new strategies, but we're not there yet. Now that being said, this isn't the fastest strategy for this one. Okay? Sometimes one of the things that you're going to realize, I'm going to erase, is that, hey, I could change things. I could change things to the same trig function in both really easy. Because I could change tangent to 1 over cotangent. Or I could change my cotangents to 1 over tangent. In this case, if I change my tangent to 1 over cotangent on this side, now the nice thing about this strategy is that my trig function's the same on both sides, so it might make things quicker. How do I get, well, still going to use that strategy. Can I get a common denominator? Can I write both sides as a single fraction? Can you see that your right side is already a single fraction? And so if I get a single fraction on this side by multiplying my cotangent theta over cotangent theta, because this is 1 over 1, I'd have a common denominator. My next step, I would write this as a single fraction. And I'm done. That was a lot faster. A lot less work. In this case, I was able, here, we're going to go down here, take this, drag it up there now. I was able to change both sides to the same trig function that made the proof faster.
So if you can, the faster way is generally to make it all in the same trig function?
That could be a faster way. Not necessarily, but in this case it was. So introduced to sort of a different strategy. Again, it's a puzzle. You're trying to make both sides look the same, but how you enter into that puzzle and what you change and how you change it is up to you. As long as you don't make up mathematics, like, or invent new fraction rules that don't exist, you're going to be fine. So this was a much faster proof as a result. Okay, questions for practice. 3, 5, 6, and 7. Aye, aye.